So another neat application. The odds are, Alex, most of you in your lifetime as adults will probably own an electric vehicle. They're becoming more and more common. Certainly all of you will interact with electric motors in some way. How do they work? A real, actual, in the industry electric motor is a little more complicated than the simplest version I'm going to show you. The simplest version that I'm going to show you has some flaws that we'll talk about, but they all share the same theory. So let's suppose we had a rigid loop of wire and it was placed in a magnetic field. So I guess the magnetic field is pointing to the right. And we're going to send a current through it. There's our battery. So you can draw in arrows. The current is going to go like that. Okay? It says, determine the direction of the current in each segment of the loop. We just did. And then the direction of the force on each segment. So first, let's look at segment 1. What direction is the current moving in segment 1? To the left? Yes? What direction is the magnetic field? You know what? These are parallel. Who remembers from yesterday, if the current and the magnetic field, or if the moving charge and the magnetic field are parallel to each other, what's the force exactly as a number? Okay, so no force on segment 1, and spoiler alert, no force if I skip one on segment 3. But there will be a force on segment 2 and segment 4. In segment 2, the current is moving up the page. Magnetic field is to the right, so I'm going to bend my hand like this. Which way will segment 2 feel a force? Into the page. What about segment 4? Okay, now Madison, we're going down my page. Magnetic field is to, okay, oh, you know what? If I go like this, my palm is pointing in the direction of the force out of the page. Well, if section 2 is being pushed into the page or downwards, and section 4 is being pulled out of the page or upwards, you know what? The loop will tend to rotate. Yes, it will tend to rotate. And now you've turned current and magnets into some kind of spinning motion. But there's a problem. The loop would rotate a half turn and then come to a stop, because once this got to this side, it would get pushed up and the other one would get pushed down. It would just kind of sit there. At best, you might be able to get it to go back and forth, but you couldn't get it to spin. So we got to be a bit more clever. But you can already see at least how we can start to get a loop of wire to want to turn, to want to spin, to want to rotate. So what do? In a simple one-turn coil motor, the simplest possible, here's a picture right here. So I'm going to zoom way in. We've got the current going this way, so on the left, the current is moving in that direction. Magnetic field lines are pointing from north to south. Every electric motor has an external magnet, although sometimes, rather than permanent magnets, you're using solenoids. What direction will the left hand, we call this loop the armature, what direction will the left-hand section of the armature feel a force? So everybody, if you want to play along with me at home, I'll face the board. The current is going up the page on the left. Magnetic field is pointing to the right. What direction will the left-hand arm of the armature feel a force? Okay, and that's why over here on the left I said it's going to feel a force in that direction. What about the right-hand side of the armature? It's going to feel a force. Point my fingers that way, but you know what? I'm kind of having to contort a little bit, but it's going to feel a force out of the page. And so, Alex, what that's going to do is going to cause it to spin, but we'd be in the same situation as up here. It would do a half turn and come to a stop. So here's what we do. What we actually have are wire brushes right here. These wires aren't connected, glued on. They have metal brushes so that this section can spin. And can you all imagine a hamburger with a bun, but no patty? So there's air instead of the patty. This piece here and this piece here are metal pieces. So what happens is this motor splits a half turn, and then its momentum carries it further until the current reconnects. Let me show you this with an animation. Sometimes an animation is worth 1,000 words. Look up. Here's an electric motor. Okay? So let me pause right here. Here's our battery. Here's the positive end. So the current is going this way, this way. Better yet, let me pause when it is right there. Current is going this way. Right here, the current is flowing away from us. Point your thumbs into my board. What direction is the magnetic field? To your left. Which way? So let's see. Current moving away from us. Magnetic field that way, to your left. This arm right here is going to feel a force upwards. Which way will this arm feel a force? Downwards. Because now the current's coming out of the page towards us, right? It's gone behind. Now it's coming back out towards us. And so it's going to spin. This gap right here guarantees that on the right, the current will always be going away from us. And on the left, the current will always be coming towards us. So let me start over. Watch. So there's the force. Right-hand side's getting forced up. Left-hand side's getting forced down. And then right here, its own momentum is going to keep it going for about 1/3 of a turn. No current flowing at all right now, but it's got enough speed to keep turning, and boom, now we're connecting again. We always have the current moving away from us on the right-hand side. We always have the current moving towards us on the left-hand side. This is a clever way, if you're stuck with direct current, to turn it into some kind of alternating current. Works great. Show you a bit of a longer animation. Okay.
The torque in a DC
so here's the idea
motor
as well. You get your maximum force when the loop or the armature is right here. Because the current is going that way, magnetic field is that way. The right-hand arm is going to get pushed up, left-hand arm is going to get pushed down.
Part of the motor. In this virtual model,
if we didn't have that gap, then the current would be flowing away from away from us on the left-hand side. We want it to always be flowing towards us on the left-hand side. We want it to always be flowing away from us on the right-hand side. And so this gap, the fancy term, it's called a split ring commutator. That's going to be in our notes in a second. Allows the motor to continue moving on its own.
Moving red balls.
For a split second, and then the current kicks in. So this motor will just keep spinning.
The current loop experiences a torque due to
you
the
want it to
offset
spin faster, add more current.
And bottom sections
or
of the loop.
make the magnetic field stronger.
Forces on the front
or
and back
add more turns
segments
of wire.
Exactly cancel.
Lots of
so
control.
They do not contribute to the net.
You want to reverse the motor, flip the current, which is pretty easy to do with a circuit.
The battery that drives this motor produces a constant voltage, which can
this
only
is how
drive
an electric
the current
motor works.
in one direction.
Except there's a problem with this design. If you shut the motor off and it comes to a stop right here by a fluke, it spins to a stop right there. Unfortunately, when you turn it back on, there's no current, so no net force, so it's stalled. So in real life, most motors have 3 armatures. One here, one at an angle this way, one at an angle this way. They're at 120-degree angles between them. If you do that, you can show no matter what, there's always going to be a net force no matter where that thing spins to a stop. So most motors have, if you look on the end, if this is where it's turning, most motors don't write this down. They have an armature like that, an armature like that, and an armature like that, and they're all spinning around a central axis. Something like that is what they'll do. So read along with me. It says this. Note the importance of the split ring commutator, that little gap right there with the brushes. Oh, also, you may hear that some electric motors are called, quote, brushless motors. Similar idea, but a different setup. And those are in some ways better because you have fewer moving parts. They'll last even longer. But I won't talk about how those work. when the armature makes a half turn, the split ring commutator makes the current in the two halves flip directions so that it's always going, in this particular example, away from us on the left and towards us on the right. We have to do that because with direct current, somehow we have to flip the current. Oh. Okay. Turn the page. Does that make sense, Clody, how the right-hand rule is used on the two arms, not the end parts, because they're parallel to the magnetic field, but the two sections of arms that are at right angles to the magnetic field, because the current is moving at right angles to the magnetic field. That is how an electric motor works. Bonus, every motor is also a generator. So if you supply current, you can get motion, but also if you spin the motor by hand, you'll get current out the other end. So this was also the invention of the generator. Question?
Why do they make the motors where why don't they just
This is the simplest possible manufacture to give you the idea. They don't build them this way. There's much more efficient, better ways to build them. And so typically what you'll find is there's a circular central hub with multiple armatures. And also they don't use permanent magnets. In fact, what they don't use an armature. What they'll actually do is they'll spin a solenoid, because why not also have your armature be magnetic? So not only is the current affecting things, but you're also getting some extra force from the magnet. Well, that's a bonus. Let's do that. So it's more complicated than I'm letting on. If you're bored, do a YouTube search. You'll find that very simple one that I showed you, but you can also look at much more complicated ones. Do a search for, I'm sure there's a YouTube video breaking down, for example, the motor in the Tesla cars. The reason that they've named the company Tesla is the motor that they're using was basically invented by Nikola Tesla, the idea. It's better manufacturing now, I'm sure, better materials, but it's the same concept. Yeah, it's really nice. Okay. A couple more applications, and then the rest of the class is yours.